Moving along, so we've done the first example, part A and part B already. So let's go on to the next example. In the next example, we have a multiple choice test with 4 questions. Each question has 5 choices for the answer. So that would be something like a multiple choice with an A, B, C, D, and an E. So you have 5 choices, but you've got 4 questions. Find the probability that you answer the first 3 questions correct. So we're not really caring about the last question. So we've got that the first question needs to be that you get it correct. The second question needs to be correct. The third question needs to be correct. I'm going to put an A for the last one, can be anything. And again, the idea, just like before, is that we've got 4 different things going on, and we're going to stick the word and in between all of these because we want all of these to happen at the same time. So let's take a look at this first question. If you want to get the first question, well, we said that just if we look at one question, that there were a total of 5 choices for the answer. So let's start there. There are 5 choices for the answer, the A through E. So for that first question, we've got 5 choices. Now remember that when you do a multiple choice test, there is only one correct answer for each question. So that if I want to get that first question correct, there's only one way to do that. I choose the correct answer. Now the second question is a new question entirely, but there's still 5 choices. And there's still only one of those 5 that's actually correct. And the same thing for the third question is there's still 5 choices and still only one of them's correct. And they don't actually tell me what I want to do with the last question. It could be anything. I could get it right, I could get it wrong. So there are still 5 choices. But here's the difference with this last piece. The last piece, the fourth question, they didn't say anything. So it could be anything. I could get it right, I could get it wrong. So any of the 5 options are okay to choose from. And just like before, I'm multiplying all these probabilities together. So let's see what happens when we multiply these all together. Well, multiplying straight across the top, I get the 1 times 1 times 1 times 5, which is just 5. And on the bottom, I get the 5 times 5 times 5 times 5 times 5, which is a total of 625. So my final answer is the 5 divided by 625. And again, I'm not going to worry about reducing this, but I am going to worry about turning this into a decimal, which is 0.008. That's my probability and my final answer. Okay, now let's find the probability for part B, which is we have 4 questions, and they're saying on this last one we don't want to answer any of the questions correctly. So we want them all to be wrong. So this time we're looking at the probability of getting all 4 wrong. So, well, let's think about this. Just like before, there are 5 total answers on each question. So there's 4 questions, and each of them have 5 choices. How many of the choices, though, in this case, are actually wrong? Well, there's only one right one, the other 4 are wrong. So that will be 4 out of 5 on each question are wrong. And again, just like before, we're going to be multiplying all of our probabilities. So to multiply these fractions straight across the bottom, we already know 5 times 5 times 5 times 5, 4 times is 625. And on top, we've got the 4 times 4 times 4 times 4. The 4 fours is 256. Divided by our 625 is, let's see, 0.4096. And that's our final probability. Notice this means if you were just guessing on a multiple choice test of 4 questions or a quiz, a pop quiz, because you didn't study, that means your chance of getting, not failing, but getting a 0%, if you were just guessing and you didn't prep for class, your chance of getting a 0 on a multiple choice quiz like this would be of almost 41%. That is really telling and kind of scary if you're a gambler and you're worried about your grade. Let's take a look at one more similar problem. The Teletronics company manufactured a batch of 400 backup power supply units for computers, and 8 of them are defective. So right off the bat, we have a total of, let's see what they said, 400 units that we're looking at. And of those 400 units, they tell us that 8 of them are defective. So 8 are defective. The next part says that we're going to randomly select 3 of the units. So we're going to select 3. What is the probability that the entire batch will not be defective? So I want all 3 not defective. So eventually what I'm going to be looking for is that all 3 are not going to be defective. Notice the other thing that they tell us, again, it's subtle and I have to keep on reading, but it's super important, is that they are made without replacement. So when I look at this problem, my thought is that I want 3 things to not be defective. So the first thing needs to be not defective. The second one needs to be not defective. And the third thing needs to be not defective. And just like before, the key word in between all these is the word "and," so that I know what operation I'm doing. Well, let's take a look. Well, the probability for this first thing that I'm selecting to be not defective, well, you have to be careful here. If 8 out of the 400 were defective, what that means is that the other 392 were not defective. So that means the chances of the first one being not defective is the 392 out of 400. Now, we said this before, is we chose something that was not defective. We are not replacing it, so it is gone. So when I move on to my second thing being not defective, there are now only 391 not defective items left, and there are only a total of 399 units total left. Now you've chosen 2 units out that were not defective. Now I still have to look at my third. Well, my third one now I've only got 390 to choose from out of the total of 398. And we're multiplying. And so let's see what this is going to mean. We're going to have a pretty large fraction here. We got to multiply straight across the top, the 392 times the 391 times the 390. That is going to be a large number no matter what. And it ends up being really large. It is 59,776,080. Assuming I did that right, let me double check. Yep. And then we still have to do the same thing for the bottom. We have to multiply out the 400, the 399, and the 398. 400 times 398, 400 times 399 times 398. And I'm getting 63,520,800. And then to get my actual probability, I need to take these 2 and divide. So I need to take my 59,776,080 and divide that by my 63,520,800. And I get 0.94. And what that means as my final answer is that my probability of getting the entire batch not being defective is that your chance is 94%.